Hello, grade 12s. In today's lesson, we're going to be looking at momentum and impulse questions, and we are tackling graph questions as you have requested. So without any further ado, let's get right down to the lesson. So now you know the strategy. We said you check and see if there are any definitions, and if there are any definitions, you just quickly run to them, deal away with the definitions before you forget them. So we are given 4.1. It says define the term momentum in weight. Let's check that. What is it? We say momentum is the product of an object mass and its velocity. Right. Now we have 4.2. It says state the principle of conservation of linear momentum in weights. Again, we have principle of conservation of linear momentum states that the total linear momentum in an isolated system is conserved or remains constant. Nice. Now let's look at 4.3. It says show by means of a suitable calculation that the ratio of the masses of the two objects, mass A to mass B, is 4:3. Right. Now before we show that, let's come to understanding the graphs here. We can see that if your velocity is here, the velocity versus time graph, if you are given a velocity versus time graph, the velocities that you're going to see on the y-intercept, they indicate your initial velocities, right? So that means the velocity of initially of A is 4 and the velocity of B initially is -1. Then the ones that you're gonna get throughout, those are your final, right? Now let's come to understanding what is happening here. If you see a drop there, so you can see the bold line there of A is dropping at this point, right? What does it indicate? It indicates that at that particular moment or at that particular instant, the collision is taking place, right? But then now there are two types of graphs. You can either have a graph like this or have a graph that is slanting like this. What is the difference between these two graphs? Now with this one, you can tell that the collision is what is elastic, right? Why do we say the collision is elastic? Because we can see there is no contact time in between the objects, right? So that means no energy is lost in the process. So this is elastic, no contact time, no energy is lost during the process. But if you look at this second one here, you can see that the graph is slanting during that period of collision. So that means this is the graph for an inelastic collision, right? So once you see a graph that is slanting like that, you already know that the collision is inelastic because of what? There is contact time in between the objects. So the force is in contact with the object, and then now there is a loss of energy during the collision, right? So in this case, remember, an elastic collision, we say this is where both momentum and kinetic energy is conserved. But with inelastic collision, this is where now we have momentum is conserved, but the kinetic energy is not conserved, right? Awesome. Now let's try to answer that question. It says show by means of a suitable calculation that the ratio of the masses of the two objects is 4:3. Now we know for a formal question like that requires mass, we know that we need to consult the principle of conservation of linear momentum, whereby now we'll say that sum of momentum initially is equals to sum of momentum final. Now we have mass of A multiplied by its velocity initially, and then we have mass of B multiplied by its velocity initially. And again we have mass of A multiplied by its velocity finally, and then plus mass of B multiplied by its velocity finally. Now let's substitute. We can see that from the statement we are not given any masses, right? So we just need to write this as MA. You just need to trust the process of maths with this one. Now, what is the velocity of A? We are given that it is 4. Extracting it from the diagram here, right? We can see that it is 4, right? Now plus M of B, and then extracting it also from the diagram, we can see that it is -1. initially, that's -1, right? Then we have mass of A. Again, we don't have the mass of A, but then we have the velocity of A. Extracting it from there, we now have that after the collision, it is 1, right? So after the collision, the velocity is 1. Then the mass of B and the velocity of B now after the collision, it is 3, right? Now let's do that. We have MA times 4, which gives us 4 MA, and then MB times -1, that's negative MB, and then MA times 1, it's MA, and then we have MB times 3, that's 3 MB. Then now what do we do? It's just now a matter of arranging them in terms of the like terms. So now we have 4 MA. If we transpose that 1, we have minus MA. And then now we have 3 MB. If you transpose it to the other side, now it's MB. So 4 MA minus MA is now 3 MA. And then 3 MB plus MB is now 4 MB. But now remember, they said the ratio should be MA to MB is 4:3. Now, how do we get to that, since now we see that this is 3 and 4, right? Now, if you can think of it in terms of the LCM, between these two numbers, 3 and 4, what is the LCM of 3 and 4? The lowest common multiple of 3 and 4 is 12, right? So remember, these two have to be equal. So now, in order for them to be equal, you say, what number can you multiply MA3 with so that this whole thing gives you the LCM 12? So we understand that you'd have to multiply MA by, you'd have to multiply 3, I meant to say by 4, right? And now, what is the number that you can multiply to 4 so that it gives you 12? So you understand that you'll have to take this 4 and multiply it by 3. And in that way, you now have your ratio, the ratio of the masses. Remember, these are the masses we are talking about. So the ratio of the masses is 4:3, right? Awesome. Now we have 4.4. It says draw vector diagrams not to scale to illustrate the relationship between the initial momentum, final momentum, and the change in momentum for object A. Now for object A, this is what we're going to have now. So for object A, we're going to say the momentum, what was the direction of the momentum of object A? So object A was going to that direction. So this is initial, right? And now object A is also the momentum, the momentum is in which direction again? The final momentum is also in the eastward direction. So we have PF, right? Then the change in momentum, we have to add the two because they're going in the same direction. So we say change in P, right? So that is the relationship between the initial momentum, final momentum, and change in momentum of object A. So initially it was going east, and then also finally did not change the direction. Remember, it only changes the direction if now it jumps the x-axis, right? So when it does not cross this line, the x-axis line, the 0 line, it has not changed the direction, right? So from A up until this point, we say it has only slowing down, right? So we see a slowing down, a deceleration there, but then it has not changed the direction of motion. But if we look at the graph of B, object B was going westward, -1 at -1 meters per second. Now, after the collision, what happened? It now changed the direction. So after the collision, this is what happened. So this was the object going B, and then now after the collision, then it goes that that side, right? So it bounces and then goes to the right. So how do we see that? Because it has jumped the x-axis line, right? So if it jumps the x-axis line, that means it changes the direction. If it doesn't jump the x-axis line, then it does not change direction. Okay. So for question 4, it says trolley X of mass 1.2 kg travels at 8 meters per second east and collides with trolley Y of mass 0.5 kg, which is initially at rest. Now 4.1 says state the principle of conservation of linear momentum. So we want to quickly run to the definition and deal away with it. So we now have principle of conservation of linear momentum states that the total linear momentum in an isolated system is conserved. Awesome. Then for 4.2 says now calculate the magnitude of the velocity of trolley Y immediately after the collision. And how many marks are we given? 4 marks. Now we know there is a hint there. We have already stated the principle of conservation of linear momentum. That means we'll have to use that. Then we calculate the velocity. Now let's understand our initial velocities. This is for trolley X, right? Our initial velocity is 8 meters per second, right? So that's VI, collecting our data. Then our VF, now you can see that after the collision, what is happening? You can see the graph is slanting here. So after the collision, we have 4 meters per second, right? So for the fact that it is slanting, we now know that this is an inelastic collision, right? Because there is contact time there. Now, let's calculate. We are given the information for trolley Y there. They say it has a mass of 0.5 kg and it is initially at rest, right? So initially at rest tells us that the velocity is 0. So having to calculate that, let's say now we have sum of momentum initially is equals to sum of momentum final. Again, we have m1 v1 plus m2 v2 is equals to m1 v1 now finally and m2 v2 final. Now what is the mass of object 1? If we take object 1 as trolley X, that means the mass is 1.2, right? So we have 1.2 and the velocity initially is 8, and then the mass of object 2 is 0.5, and then the velocity they said initially at rest, so that's 0, and then now we have 1.2, but the velocity finally of trolley X is now 4. Then we have plus the mass is 0.5, and then we have v2 like that. So that's what we are looking for. We are looking for the velocity of trolley Y, the collision. Now we have 1.2 times 8, that gives us 9.6. Then 0.5 times 0 is 0. Then 1.2 times 4, we have 4.8. Then plus 0.5 v2. So now at this point, what are we supposed to do? Transpose 9.8, 4.8 I mean. Then 4.8 is equals to 0.5 v2, right? Now we have 9.6 minus 4.8 is 4.8 equals to 0.5 v2. So we divide both sides by 0.5, divide both sides by 0.5. Now our v2 is 9.6 meters per second. Right. Now 4.2.2 says calculate the average net force that trolley X exerts on trolley Y during the collision. So now to calculate the average net force, we know the formula that we have for this one is the formula that we have. So that's 4.2.2 is F net change in T is equals to change in P, right? So we know that one is what we call the impulse momentum theorem. Then for this one, we go VF minus VI and then change in time. So now what do we have? So that's the formula. The mass, what do we have for the mass? It's 1.2. And the velocity finally is 4. And then we have minus 8. So we are tackling this one in reference to trolley X, right? Then change in T. What is the change in T? So the collision, this is the time of the collision, right? This is the time it takes for the collision to happen, or the time in which the net force is acting on that object. So we have 20.1 to 20.2. So we're going to just write it as that. Remember, it's change in time. So we have 20.2 minus 20.1. That is just 0.1. So in between that. So if you punch that in your calculator, you now have negative 48 Newton, which we can now conclude that F net is equals to 48 Newtons. Awesome. Now 4.3 says, is the collision elastic or inelastic? Explain the answer by means of a suitable calculation. Now looking at the graph, we can already see that the collision is inelastic. But now it's a matter of having to calculate, because we cannot just say inelastic and get that whole 5 marks. So we must explain by means of a suitable calculation, right? So now to calculate that, we know anything that pertains to elastic or inelastic collision, we have to now calculate it using the sum of EK, right? So we say sum of EK initially, then we'll have to compare it with the sum of EK finally. If they are equal, elastic collision, that means no loss of energy. If they are not equal, that means inelastic collision, because there was a loss of energy. Now let's calculate it. Half mv squared initially plus half mv squared initially also. So this is for object A and this is for object B. Now we have half. The mass of trolley X was 1.2 and its velocity is 8, and then square that plus 1.2. The mass is 0.5, and then the velocity initially was 0. Remember, they said it's at rest. Then if you punch that in your calculator, we have 38.4 joules, right? Now let's calculate the sum of EK finally. Now again, we have half mv square plus half mv square. So this is for A, this is for B. Now trolley X, the mass is 1.2 and its velocity finally is 4. We can get it from the diagram. And then the mass of trolley Y, 0.5. But then the velocity finally, we have just calculated it in the previous question. That's 9.6. So if you punch that in your calculator, what do you get? We have 32.64 joules. Now from this, what can we conclude? We can conclude that the collision is inelastic. Why? Because we can see here the EK initially is 38.4 joules, but the EK finally is 32.64 joules. So there was a loss of energy. Therefore, we say sum of EK initially is not equal to sum of EK finally. That's how you conclude on that. Now let's look at this question 3. It says car P mass M blah blah blah. Now remember, we need to define the term impulse in weight. So we quickly run to the definition. So 3.1 says define the term impulse in weights. So we have impulse is the force of the net force, is the product of the net force. Impulse is the product of the net force acting on an object and the time the net force acts on an object, right? Now for 3.2, it says calculate the velocity of car Q after the collision. Now let's observe what is taking place here. This is the graph. Car P mass M is initially traveling eastward. When it collides with another car Q of mass 1.7 m, that means car Q has 1.7, it's 1.7 times the mass of car P. So that's why it's 1.7 m, right? So that means car Q, we can say now that car Q is 1.7 times car P, right? Remember, car P is m, so that makes it 1.7 m, right? So I think we all understand that. Now they say which is traveling westward at 15 meters per second. So car Q, so we have, let's say VA is 10 meters per second. So initially, but then VB initially is negative 15 meters per second. Why negative now? Because it is traveling in the opposite direction, westward. Ignore the rotation effects of the wheels and friction. The graph below shows how the velocity of car P changes with time. Take the initial motion of car P as positive. Now, they say define, calculate 3.2, calculate the velocity of car Q after the collision, right? So what do we do now? For 5 marks, we can see now that we need the conservation of linear momentum formula, right, in order to calculate car Q. But now let's understand the graph. What is happening here? We can see that the car P was traveling eastward, and then the collision took place here. What collision is this? From the graph, because it is slanting, we say it is inelastic. But then now we can see that this collision is taking place and then it crosses the x-axis. When it crosses the x-axis, what happens to car P? It tells us that now car P is moving in the opposite direction. So this -5 now indicates that the car has changed the direction of motion. So once you see the line crossing the x-axis line, remember that is a change in the direction of motion. So now let's get to 3.2. So for 3.2, we say sum of momentum initially is equals to sum of momentum final. So we have mass of, let's call it 1 and V1 plus M2 V2. Then M1 V1 plus M2 V2. So we can see the objects are separate, right? So that's why we have formulas like that. Then what is mass 1? So we are given that the mass, we are not given the mass. It's m, right? And then what is the velocity? It's 10. We can extract it from the graph here, right? Remember, your y-intercept here indicates the initial velocity. Then we have mass of 2, it's 1.7 m. And they said the velocity is moving 15 meters westward. So because it's moving westward, it has negative. Then here we have again m. And then what is the velocity? Finally, it's -5. Then plus 1.7 m. And then what is the velocity? We are looking for that velocity. So we have V2. Then what is m times 10? We have 10m. So now you don't have to worry about the m's there. Just trust the process of maths, right? Then we have 1.7 times -15. That's -25.5 m. Then we have m times negative 5, that's negative 5m. Then here it's plus 1.7 m and then V2, right? At this point, you can see you cannot add this negative 5m and this 1.7 m because now here this one has a multiplication sign, and that is that is combined with V2, right? Now that means we have to say 10m minus 25.5. That gives us so having to calculate that, we now have negative 15.5 m, and then if we transpose the negative 5, we have plus 5 m equal to the one that is left there is now 1.7 m dot V2, right? Then what is negative 15.5 plus 5m? We now have negative 10.5 m, then equal to 1.7 m V2. So now what do? Divide both sides by 1.7 m. So you can see that m has now cancelled out. Then we have V2 is equal to negative 6.18 meters per second, which you know to conclude that means that V2 is 6.18 meters per second to the west, right? Let's move along. Now 3.3 says it is observed that the kinetic energy of the system decreases by 175,000 joules after the collision. 3.3.1 says, is the collision elastic or inelastic? So remember, we can see a keyword there, decreases by 175,000 joules after the collision. If the kinetic energy decreases, that means it is not conserved. It's inelastic, right? But also from the graph, we have observed that from the graph, what do you see there? It is slanting. So that means it is inelastic. There is contact time with the object. Then 3.3.2 says calculate the mass m. Calculate the mass m. Now for 5 marks, there is a hint there. They spoke about energy, and then we have 5 marks. So that means for this one, to calculate mass m, we now have to consult the sum of kinetic energy. So let's say sum of kinetic energy initially. Let's calculate that. We have half mv square plus half mv square. Then this is half, and then we have our m again. But what is the velocity? Initially, we have 10. And then again, for the mass of B, we have 1.7 m. And then what is the velocity initially? It's negative 15, and then square. If you punch all that in the calculator and add, we have 241.25 m, right? And that is the sum of EK initial. Now remember, we have to compare that with the sum of EK finally. So let's calculate sum of EK finally. So now we have half mv squared plus half mv squared. But remember, they said the system decreases by 175,000 joules, right? So what are we supposed to do with that 175? Because it will be lost, then that means we have to add it here, right? On the final side. Remember, it is lost from initial. Initially, when this thing is colliding, it had that energy of 175,000. Now it is lost finally. There is a loss of energy, therefore we indicate it on the final side. So if we had to indicate it on the initial side, we'd say sum of EK initially minus 175,000. But now if we indicate it on the final side, we say sum of EK finally plus 175,000, right? So to indicate that it is lost in the system. So that's 175,000, right? Then now we have half the mass is m, and then the velocity finally is -5, remember. Then half the m is 1.7 m, and then the velocity finally we have calculated it to be -6.18, and then remember to square it, then plus that 175,000, right? So now having to punch that in the calculator, we have 44.76 m and plus 175,000, right? So because now we want to calculate m, what do we then do? So let's say this is equation 2, and let's call this equation 1. So at this point, we have to do what? We have to equate the two equations, because we are saying the EK initially, this is the sum of the EK initially. But then now it will only be equal to the sum of EK finally if we add that energy that has been lost there, right? So adding that energy that has been lost, 175,000, on the final side makes the EK initially, sum of EK initially, to be equal to the sum of EK final. So now this is how we now have it. We say sum of EK initially is now equal to sum of EK final, right? But with that 175,000, right? So what is that EK initially? We found that it is 241.28, right? And the sum of EK finally is 44.76 m. That's just it. That's the sum of EK final. Then plus 175,000 that is lost in the system during the collision. So we have m here. Now transposing it this side, we have 241.28 m minus 44.76 m is equals to 175,000, right? Then if you calculate that one, it gives you 196.29 m, which is equals to 175,000. At this point, what do you need to do? You divide both sides by 196.29, divide 196.29. Then what is your solution here? Punch that in your calculator. We now have the mass is equal to 891.54 kg, right? Now 3.3.3 says, using the graph, calculate the magnitude of the net force exerted on car P during the collision. So now the correct graph was supposed to touch here, and then also goes all the way to, so let me draw it. So it was supposed to touch at 1.25 and also touch at 1.75 according to the errata. So if you are practicing with Free State 2022, then note that mistake there. Then 3.3.3 says, using the graph, calculate the magnitude of the net force So we know what formula do we use to calculate the net force is the impulse momentum theorem or momentum impulse theorem, then of the net force exerted on car P during the collision. So this is how we go with this one. So we say now F net change in T is equals to change in P. That's the formula as it is. But now we are looking for F net, so we can just manipulate it to be change in P over change in T, making F net the subject of the formula. Now, if we check it in reference to this object M, right, car P, this is what we're gonna have. So in reference to car P, so this is in reference to car P, and we have M is equals to VF minus VI, and then change in T. Then the mass, we have calculated the mass M to be 891,54. Then the velocity finally of car P is -5, and the velocity initially is 10, right? So we have -10. And then the change in time, remember I said the collision is happening between 1.75 and 1.25. So you have 1.75 minus 1.25, and then punching that in your calculator, now your F net is equal to 26. So that's a negative 26,746.2 Newton. But then you have to now say F net is equals to 26,746.2 Newton, right? So since it is the force that is experienced by car P, this force is going west. So this is the force it experiences from the other car, from car Q, when it collides with it. So calculate the magnitude. So there's no need for direction also, because they said magnitude. So you can just come here and erase the direction. Remember, when it says calculate the magnitude, you are only required to give us the size and not the direction. So that's how you could have tackled the question. All the best in solving these questions. Ra.